Now today I will discuss about surface integral. This is a very important chapter of vector calculus. You have to evaluate this kind of surface integral. You are given a vector function f and ds. This is very important. This has to be evaluated on a surface S. This surface S can be open, it can be closed, right? So I'll discuss with you how to evaluate the surface integral. Surface integral is the integral evaluated over the surface. S can be a part of hemisphere, it can be a cone, it can be a plane surface, it can be any kind of surface. So here the domain of integration is the surface. Let me take an example of a surface. We have to write this ds in terms of dx dy. Alright, so let me take the projection of this ds also. Let me take the projection of this ds also. So this will be written as, this is the projection. This is ds and this is dx and this is dy. So let me correlate this ds and dx dy. Let me correlate this dx and ds dy. If I draw this ds can be drawn like this, and say this can be your ds, this can be your ds, or let me draw it much better way. Your ds can be, say this. So this is your n and this is your k. See, this is your ts, right? This is your ts and the projection is dx dy. This is dx dy. So can you see that this angle theta and this angle theta will be same? This theta and this theta will be same. You can see it here. This is theta. Now this will also be theta. This is perpendicular. This is also theta. I show it once again, right? See, this is theta. This is 90 minus theta. So this will be theta and this will be theta. So in the same way, this theta and this theta will be same. See what happens when you take the projection of ds on xy plane. See, one of the dimension contracts. If you take projection on xy plane, this dimension is going to contract and become dy. This dimension, if this is say dl, this is dy, so dl cos theta is dy. This dimension will remain same. This dimension will remain same. One of the dimension will contract and you will have ds cos theta equals to dx dy. You can see it from here. ds cos theta is dx dy. The projection of ds on xy plane is dx dy. So I can correlate ds and dx dy. So this is ds cos theta as dx dy. Now what is cos theta? See, cos theta can be written as, this is two vectors, two unit vectors. So I can write cos theta as n dot k, or I can write ds as dx dy upon n dot k. Similarly, if I take projection of ds on yz plane, this ds will be written as dy dz n dot I, and if I take projection on xz plane, it comes to be n dot j. So this is how dx can be converted into dx dy. So this gives us a very important way of evaluating this surface integral by converting it to a double integral. See how we can convert it to a double integral. Let me rub this portion. So this comes to be, see, on if I take projection on xy plane, this converts to f dot n dx dy upon n dot k. And what is n? How you find n? So this is s. So you have the equation of surface also. That equation of surface s is, say, fxyz equals to 0, or say some constant c. Then your n can be found by simply you take gradient of s and divide it by its magnitude. So this will give you n. This will give you n. This is the equation of surface. You have to write equation of surface as fxyz and equate it to a constant. So this gradient of this function f divided by its magnitude will give you n. So this is how we convert a surface integral into a double integral. This is the only way of this is the way, I won't say this is the only way, but this is a direct way of solving a surface integral by converting it to a double integral. Similarly, I can convert it to a, if I take this is when I take projection of s on xy plane, and remember this double integral has to be evaluated on the region R. What is R? R is the projection of s on xy plane. See, the domain of integration of surface integral is s, whereas the domain of integration of double integration is the projection of s, that is R. You have to evaluate this double integral over R. And one more thing, see, for evaluating this double integral, the integrand is f dot n upon mod of n dot k. That's the integrand. Integrand should be a function of x and y. But sometimes you get the integrand also contain a variable z. See here the independent variables are x and y. I have to integrate this with respect to x and y. Sometimes this particular quantity, this one, involves z variable also. So you please remember, you should not put z equal to 0, because you should not put z equal to 0. You will have an intuition that since I am evaluating over r z is 0, but you don't put it at z equal to 0. What you do is you replace z, you write z in terms of x and y using this equation of the surface. Suppose the equation of surface is z equal to x square y square. This is a paraboloid. So if this particular integrand contains z coordinate or z variable, you replace z with x square plus y square. If suppose the surface is a hemisphere like this, so you should replace z with a square minus x square minus y square. You please note this point, this is very, very important. So whenever your integrand contains a variable z, you replace z or you write z in terms of x and y using this equation of the surface. Now if you take projection on yz plane, this comes to be f dot n dy dz n dot I. Similarly, if I take projection over xz plane, this comes to be dx dz n dot j. This is how you write. This is how you write n dot j. So this is how we can evaluate the surface integral. We can evaluate the surface integral by converting it to a double integration. And then we can evaluate this double integration over the region which is the projection of the surface S on the corresponding coordinate plane, right? So I'll take one example. This will become very clear to you how do we evaluate the surface integral.